Well, for our second talk today, we're joined by Andrew Nugent, who's going to be talking about opinion dynamics with continuous age structure. Take it away, Andrew.
Okay. I get straight into PE models for opinion dynamics. So the opinions are just going to be one-dimensional variables between -1 and 1, representing how much you disagree or agree with something. They're mostly going to evolve by a person with opinion X interacting with a person with opinion Y. And then their interaction has this form. So the person with opinion X is going to move towards opinion Y, and the amount they move is going to be described by this interaction function, but it's a function of the distance. The idea being that if the opinions are relatively close, then you might move further, and if the opinions are quite far apart, then they might ignore each other. And what we're interested in is not the opinions of each individual person, but this population level density that basically says at time X, what's the probability that a random person, no, at time T, what's the probability that a random person has opinion X? And that evolves according to this PE. So the first part, it just says it evolves in time. This bit is those interactions. So if we're looking at opinion X, we integrate over all the other opinions that they could interact with. We look at the probability of someone having that opinion and then what the effect of that interaction would be. And then we also have some opinion diffusion that is sort of modeling random changes in people's opinion distribution that causes this density to kind of spread out slightly. Okay, so for some examples, I'm going to look at an interaction function that is 1 if x minus y is smaller than a given radius, and then 0 outside that radius. And so the width of that interaction radius determines what happens. If it's very large, then everyone is basically willing to interact with each other. And we initially get sort of 2 small clusters that then combine into 1 cluster, and everyone agrees at a consensus value in the middle. And the size of this diffusion determines sort of how smooth this distribution is at the end. If we make the interaction radius a bit smaller, then these 2 clusters become separate and they're a distance apart, where basically the people in this cluster aren't willing to interact with the people in this cluster, but each of them forms sort of their own peak. And if we make the interaction radius really tiny, then we stay very close to this initially uniform opinion distribution. There's a bit of sort of a wiggle at the end, basically, because of the boundary conditions. So people can't diffuse out of -1, 1. So it's kind of like if you give someone a survey and say between -1 and 1, how much do you agree with something? They can't give an answer of 1.1. They have to stay bounded within this region. So the people at 1, everyone that they interact with has an opinion less than theirs. So they're going to move in slightly. And that's why you get this little dip and this little peak here. But it's not really an opinion cluster. They're not kind of clustering together like in the earlier ones. It's just sort of accounting for the boundary conditions. Okay. So why do you add age structure to this? There's a few kind of, well, the first reason is that people do age. So it kind of, it makes it more realistic because it's a thing that actually happens. It gives a sense of time to the model. So you sort of get, it gives an idea of what a person's lifetime is. So looking at one individual, how does their opinion change over their life? But also means that you have, this is kind of skipping to the bottom one, you kind of have this ongoing kind of situation. You don't just have a fixed population of people that discuss their opinions for a bit and then reach a consensus and just stop. You kind of have this continual process where people are aging and dying and new people are entering the population with new opinions. And your process kind of continues to be dynamic for a long time. You can also introduce some sort of the idea that people of different ages might interact in different ways. So you might be more likely to respond to people that are a similar age to you, or you might respect the opinions of a particular, like, I don't know, if you're talking about some new technology, you might respond more to opinions of younger people who might be more familiar with it. Yeah, I'm kind of interested in the long term, if you have kind of a population that is at consensus or a population that is split into different groups, whether that situation is kind of stable or if in the long term, as new people enter, they might bring together existing groups, or your consensus might kind of break up, or it might shift. So how do we include this in the model? We now have two states, the opinion X and the age A. This U is just still -1 to 1. I'm just calling it U because it makes the notation later nicer. And ages are between 0 and a maximum age A. 0 doesn't have to actually be a person being born. It's just the age at which people enter the discussion on whatever the topic is. And that maximum age A is sort of fixed. We assume that everyone lives until that age and then dies and then re-enters the population at age 0. You can have instead that people die randomly, and you can tweak this model slightly to account for that. And again, we'll look at this joint density now. So at a time t, the probability of finding a person with age A and opinion X. And the PDE looks very similar to before, except with a few extra terms. So we have this term, as well as time evolving, everyone evolves at a constant, everyone ages at this constant rate, tau. And now, as well as interacting with other opinions, you also interact with other ages as well. And we have this function M that describes how much a person with age A listens to a person with age B. And the rest of it is the same. Oh yeah, we also still have the same boundary conditions on plus or minus 1. But we also need a boundary condition for ages. So this integral is measuring the volume of people that are leaving the population. So they've reached age A and they're leaving the population. This says how many people are leaving. And then this describes the opinion of people when they join the population. So we assume that when people enter the population, they have a random opinion, and this mu is the opinion distribution for people joining the population. Okay, so first example, in all of these three, I'm putting this M to be equal to 1. So everyone interacts the same regardless of their ages. And again, the interactions between different opinions are going to have this cutoff. So if the cutoff is kind of small, we still get 2 clusters like we did last time. What I'm plotting here is at each time point, you have a joint distribution over age and opinion. I'm integrating it over age to give like a population level opinion distribution. So this is at a particular time t, the sort of total population opinion distribution, and the color is the density. So we're starting off with it being uniform, and again, it's kind of forming into 2 clusters in broadly the same way that it did before. If we make the interaction radius larger, last time this gave us consensus, everyone just in one central cluster in the middle, but this time it does something a bit more complicated. So like if you look at just this sort of the first bit of this, you get the same kind of thing. So your population forms into 2 clusters and then they combine into 1 cluster. And for like a period of time here, basically everyone is at this consensus in the middle. But you then have this effect of new people joining the population. So if people join the population nearby the central consensus, then they just join the central consensus. But if they join the population with a more extreme opinion, then even though this interaction radius is large, it doesn't cover the whole space. So if you join outside this kind of central area, then these people here form their own more extreme opinion clusters. And if this only happens because people are joining the population, if new people didn't join the population, then everyone that started over here does end up in the central consensus. But you get these new, smaller, more extreme clusters emerging because not everyone that joins the population joins this big central group. Okay, so when the radius was small, we had 2 clusters. When it was bigger, we had a central cluster and 2 kind of extreme smaller clusters. And then when it's in between, we get this funky behavior. So this is a much longer time period. So this is up to 60, and this is like a couple of hundred. So it starts the same as before. You get to 1 central consensus, and then you form these more extreme clusters. But in this case, the interaction radius is just big enough that the extreme clusters end up merging into the middle. And then everyone is at consensus in the middle for a bit, but people join the population at the extremes again, and then everyone merges into a consensus. And this sort of keeps going. And it appears to be periodic. I can't prove that it's periodic, but it definitely looks periodic. And it makes sense that this would happen, that you would have this big group in the middle, people that join at the extremes form their own group, and then at some point there's enough kind of connectivity between them that they all kind of compromise and come together. But then you again kind of have this vacuum at the extremes where people that enter at the extremes don't join the central group. They form their own groups for a bit and then they come together. Yeah, I don't have a plot of it here, but you can also get stuff where this central group sort of shifts to the left or right if these merges aren't quite symmetric. Okay, so yeah, that's kind of the behavior of the model. I'm going to focus now on sort of the long time behavior at the end and sort of the stationary distributions that you can get with this model. So we want stationary distributions so we can get rid of this time evolution term. And now we're looking for a solution to this equation for a density over ages and opinions that is stationary. And to make things a bit simpler, I'm going to assume that this doesn't depend on A. So when people of ages A and B interact with each other, the strength of that interaction just depends on the age of the person that you're interacting with, not on your age. Because it makes math a lot nicer. Okay, so we want basically to show that there are solutions to this equation, which is kind of tricky because it's a bit of a nasty equation. It's non-linear because you have a row here and a row here. It's non-local because you're integrating over both ages, other ages and other opinions. So basically the first thing I'm going to try to do is make it look a bit nicer. So this middle term here, you can take this interaction term and move it outside the age integral because it doesn't depend on ages. And then you'll get an MB times by a row. You can call that something else, I call it little lambda. And then here, your equation looks a little bit nicer. The next step is to take this other integral and also call that something else. So now we have a nicer looking PDE, and basically the nastiness has been hidden in these two terms. But this equation being satisfied and this collection of equations being satisfied is exactly the same thing. I've just taken out some of the terms in the top one and called them other things. Happy that they're the same? Cool. I'm just going to conveniently swap the order of those two to make the next bit work out nicely. Okay, so we have this one equation and we have this system of three equations. And if these three are all satisfied at the same time, then it's equivalent to the top one. But we can also view this system of three equations as sort of imagining that they are three independent equations. So this top one here, if we start with a little lambda, we can use the top equation to define a capital lambda. If we take our capital lambda, we can put it in to this PDE, which is now a linear local PDE, so a much nicer PDE than this one. We take our capital lambda and we get a solution rho of the PDE, and then the bottom we take our solution rho, we integrate against m, and we get a little lambda. So we basically have this chain from little lambda to capital lambda to rho, rho to little lambda. And if all three are satisfied at the same time, then we will end up back at the same thing. So if you think of this sort of capital F is this mapping that does all three of these things. We start with a little lambda, we define a capital lambda, we put that here, we get our solution rho, and then we use our rho to define a little lambda. And if we have a fixed point of this mapping, it means that all three equations are satisfied at the same time, which means that we have a solution to the original equation. Yeah. So basically, rather than, I'm going to show that the solutions to this equation exist by showing that there is a fixed point of this mapping. The first thing to do is to properly define the mapping, which will involve a small amount of functional analysis to pick some spaces. And then we'll find a subspace that is invariant under the mapping. Then we'll show that the mapping restricted to that subspace satisfies the conditions for Schauder's fixed point theorem, which means that we can conclude that a fixed point exists. And a fixed point existing means that a stationary distribution exists. And then we're done. Okay. Does the plan make sense? Broadly. Okay. But yeah, the conditions that it needs to satisfy are that it's convex, closed, and compact in order of how annoying they were to deal with. Okay, so we're going to start with a little lambda that's going to be a function in some function space. We're going to integrate it against phi to get a capital lambda, which will be another function in a different function space. That's going to become the coefficients for this PDE, and that will give us a solution to the PDE that will exist in some other function space. And then we will integrate the solution of the PDE to get back a little lambda and hope that after going through this process, we end up back in the same function space. Okay. So I spent a lot of my time trying to work out what these function spaces should be, and to make sure that this sort of mapping back and forth is kind of consistent. The short version is capital lambda and its derivative appear as coefficients in the PDE. So they both need to be in, they need to be kind of nice. We need to be able to differentiate capital lambda. So we need to be able to differentiate this with respect to x. So we need to be able to swap an x derivative and a y integral, which means that little lambda has to be in L infinity so that we can swap, so that we can differentiate this. If little lambda is in L infinity and we assume that the interaction function is sort of smooth, then it means that capital lambda is also going to be twice continuously differentiable, and then we can apply some sort of relatively standard theorems, because this is a nice linear PDE, to say that this PDE has a solution. The solution lives in this Sobolev space. The 2 and the 1 means that it has 2 weak space derivatives and 1 weak time derivative, and this 2 means that the solution and all its derivatives are L2 functions. And then with a bit more work, we can check that if the solution to the PDE is in this space, when we integrate it, we get back something that is in L infinity. So this is a consistent set of spaces for us to define all of the mappings. So the mapping is to go sort of through the whole loop. From there, we can then, M needs to be Lipschitz continuous. After that, we can check that this subset of L infinity is invariant under F. So if we pick a little lambda that starts in this subset K, and we go through all this, we'll get back something else that's in K. We're looking at lambdas that are positive and integrate to 1 because they're actually probability distributions, and then they are uniformly bounded in L infinity for some constant that exists, trust me. Okay, to use the Schauder's fixed point theorem, we need this subset to be convex, closed, and compact. It is convex, it is closed, but it's not compact. But it is convex and weakly closed and weakly compact. And if we restrict the mapping to this subspace, then the mapping is weakly continuous. So we can apply the fixed point theorem, but in the weak topology, to say that there does exist a fixed point of the mapping in K, which means that there does exist a stationary distribution of the PE. Okay, let's have a look at what they actually look like. The first one's a bit boring, sorry. So this is age here, so the age of an individual, and this is their opinion. The initial, when people enter the population, they enter in one of 2 opinion clusters. And actually, in this, for the parameters that we have here, if people just stay in the opinion cluster that they enter when they join the population, then that's actually stable in time. So this joint distribution is stationary. But for the same age 0 distribution and all the same parameters, this distribution is also stable in time. So in this one, when people enter the population, they are split into 2 clusters. But over the course of people's lifetimes, so as people age, they sort of reach a consensus. So basically, younger members of the population are split into 2 groups, but older members of the population form a consensus. And this is also stationary in time. Okay. So yeah, this kind of shows that stationary distributions aren't unique. I don't know when they are unique. I had a look at applying, rather than Schauder's fixed point theorem, the Banach fixed point theorem, which would say that they're unique, but basically that you would need the mapping to be a contraction, and it's not. it would also be interesting to study the convergence towards stationary distributions and to kind of classify what types of behaviors are possible in the stationary distributions. There's lots of other stuff to do as well, not to do with stationary distributions, to do with other things that I would like to prove about the PDE, and then fitting it to data, looking at different age interaction kernels, looking at people dying randomly and having a dynamic age distribution, and adding noise into the PDE to get an SPDE so that the clusters themselves move. And here are various references for the opinion dynamics bit and for the mean field limits bit. Yeah, we published this as a preprint relatively recently. And that's it. Thank you.